Hello and welcome to lecture 25 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to discuss how to obtain the Fermi level in doped semiconductors. Okay, so last time we learned that doping is a process that is used to control the concentration of charge carriers in semiconductors, the concentration of free electrons and the concentration of holes. In n-doping, the concentration of free electrons increase, the concentration of holes decrease, the Fermi level moves up. In p-doping, the concentration of free electrons decrease, the concentration of holes increase, and the Fermi level moves down. And we are denoting the Fermi level of an intrinsic semiconductor with the letter I, the Fermi level of n-doped semiconductor with the letter N, and the Fermi level of a p-doped semiconductor with the letter P. And recall that these are the expressions connecting the concentration of particles with the Fermi levels. Now in lecture 23, we found that the Fermi level of an intrinsic semiconductor lies in the middle of the band gap. And we learned that this is a consequence of the fact that the concentration of free electrons is equal to the concentration of holes in an intrinsic semiconductor. But that's no longer true in doped semiconductors. In doped semiconductors, the Fermi level depends on the concentration of doping atoms. And these concentrations, they are chosen by the engineer to obtain the properties, the electrical properties that the engineer needs. So in this lecture, we need to find an explicit expression connecting the Fermi levels of N and P doped semiconductors with the concentrations of doping atoms. And to do that, we need to define some new notation. So we're going to use Ni and Pi to denote the concentration of free electrons and holes in intrinsic semiconductors. So I for intrinsic. And of course, these concentrations are equal because we're talking about intrinsic semiconductors. So we could in principle use only one symbol, either Ni or Pi, but I prefer to keep both because then we can emphasize whether we're talking about free electrons or holes. And also recall from the previous lecture that N-doping atoms donate electrons to the conduction band. So these atoms are also called donors. So we're going to use Nd to denote the concentration of N-doping atoms, D for donor. And we're going to use Na to denote the concentration of p-doping atoms, A for acceptor, because these atoms accept electrons from the valence band. Now, before we take a look at the expressions for the Fermi level, it's convenient to express N and P in terms of the concentrations of free electrons and hole in an intrinsic semiconductor. So we want to recast this expression in terms of Ni, and we want to recast this expression in terms of Pi. Now let's begin with the concentration of free electrons. So we can take this term here and add and subtract the Fermi level of an intrinsic semiconductor. So we're adding 0, we're not modifying the expression. But if we do that, then we can break the exponential into these two parts and recognize that this term here coincides with this term in the particular case where the Fermi level takes the value of the Fermi level of an intrinsic semiconductor. So that means that this term is the concentration of free electrons in an intrinsic semiconductor. So we can replace it with Ni. Now let's suppose that we want to apply this equation here to an n-doped semiconductor. So if we're going to use this equation in an n-doped semiconductor, then the Fermi level we need to use is the Fermi level of an n-doped semiconductor. So this Fermi level here would be used here. And then we're going to get this term minus this, which would be a negative number because this Fermi level is higher than this Fermi level. So we're going to get this minus this is a negative number. So we have the exponential then of a positive number, because we also have this negative number here. So we have negative and negative, positive. And the exponential of a positive number is a number larger than 1. So that means that n will be larger than ni, because n will be ni times a number larger than 1. And that's what I expect for an n-doped semiconductor. The concentration of free electrons increases with respect to the intrinsic semiconductor. And if we apply this equation to the situation of a p-doped semiconductor, then the Fermi level here has to take the value of a Fermi level of a p-doped semiconductor. So this term here will be positive, because the Fermi level of an intrinsic semiconductor is higher than the Fermi level of a p-doped semiconductor. So this will be a positive number. The exponential will be the exponential of a negative number. And the exponential of a negative number is a number lower than 1. So now n would be lower than ni, would be a smaller number than ni, because n will be ni times a number between 0 and 1. And that's exactly what we expect for a p-doped semiconductor. The concentration of free electrons in a p-doped semiconductor is lower than the concentration of free electrons in an intrinsic semiconductor. And finally, notice that if we use this equation for the particular case of an intrinsic semiconductor, then the Fermi level has to take the value of the Fermi level of an intrinsic semiconductor. We're going to get exponential of 0, which is 1, and n will be equal to ni as expected. Now we can follow the same idea for the concentration of holes. So we add and subtract the Fermi level of an intrinsic semiconductor, break the exponential into two parts, recognize that this part is the concentration of holes in an intrinsic semiconductor. So when this term takes this value, so we can replace this term with pi, and we have an expression for p in terms of pi. And we can again test that when we use the Fermi level of an n-doped semiconductor here, then we get the exponential of a negative number, so that means that p will be lower than pi as expected for an n-doped semiconductor, because n-doping reduces the concentration of holes. And when we use the Fermi level of a p-doped semiconductor here, then we get that p is larger than pi as expected for a p-doped semiconductor. Okay, so from now on we're going to use these two expressions for n and p. Okay, now let's turn our attention to the problem of finding the Fermi level in terms of the concentration of doping atoms. Let's begin by assuming that we have an n-doped semiconductor. So there are two contributions to the concentration of free electrons. There are the free electrons that were already there in the semiconductor before we doped, so the concentration of free electrons in an intrinsic semiconductor, and there's the contribution of the electrons coming from the doping atoms. Now, it's typically the case, even though not always, that the concentration of doping atoms is much higher than the concentration of electrons in an intrinsic semiconductor. So when this is true, we can approximate the concentration of free electrons to the concentration of doping atoms. So in this approximation, we are considering that all electrons came from the doping atoms and all doping atoms were ionized. So this is not always true, but often it is true, and often this is a good approximation. So we're going to use it in our derivation. So assuming that this is true, then we can replace this term with the concentration of doping atoms. And since we are dealing with an n-doped semiconductor, we need to replace this term with the Fermi level of an n-doped semiconductor. Since our goal is to express this term in terms of this term, all we need to do is to rearrange this equation. So we pass the ni dividing, take the log on both sides to get rid of the exponential, and then rearrange to find this expression for the Fermi level of an n-doped semiconductor. And notice that the higher the concentration is, the more the Fermi level is raised with respect to the Fermi level of an intrinsic semiconductor. So this expression, especially this term here, teaches how much the Fermi level increases with respect to the Fermi level of an intrinsic semiconductor. And recall that this expression assumes this condition. So it's only valid in an n-doped semiconductor. And if you want to find now the concentration of holes in an intrinsic semiconductor, we could use this expression here, replacing the Fermi level here with this term, and we would have this term because we in principle know ND, because this is a parameter that we control, we choose it. So once we chose ND, we can find the Fermi level, we can find this concentration, and we can find this concentration. Now if you have a p-doped semiconductor, we can follow a similar line of reasoning. Typically, but not always, the concentration of p-doping atoms is much higher than the concentration of holes in an intrinsic semiconductor, and that lets us approximate the concentration of holes to the concentration of doping atoms. So we can use Na here. This is the Fermi level of a p-doped semiconductor, so we can solve for this term. We get this expression, which is teaching how much the Fermi level of a p-doped semiconductor lowered with respect to the Fermi level of an intrinsic semiconductor as the concentration of doping atoms increases. And recall that this expression is only valid if this condition applies, and this expression is only valid if this condition applies. If these conditions are not true, then we need a more sophisticated treatment, but this is outside the scope of our course. But our simplified treatment is often it can be applied, and it already captures the essential physics. In an n-doped semiconductor, the Fermi level increases with the concentration of doping atoms. In a p-doped semiconductor, the Fermi level decreases with the concentration of p-doping atoms. And with that, we conclude chapter 2 of the textbook. So in the next time, we're going to start looking at p-n junctions. So I see you there.